So last time we discussed the motional EMF, which is a thought experiment where we change the area of a rectangle loop in order to change the flux to induce current in a closed loop. Okay, this is a thought experiment because we calculate the numbers, right? Even if you want light up a light bulb with 1.5 watts, okay, you're gonna move the bar at 300 meters per second. Okay, so that's why it's only a thought experiment. You're not gonna really do that in real life. Okay, but it was a good exercise to practice Faraday's law, Lenz's law again, and also we confirmed that we also reviewed conservation of energy. We confirmed conservation of energy because the electric energy is going to be equal to the work done by the external force. Okay, so that's what we did last time. But again, then what is the practical way to generate electricity in real life, right? Because I said we do use ENM induction to generate electricity in real life. But these two methods we have discussed so far, right? Because if you want to generate electricity in real life, you have to have magnetic field, and then you have to change the flux through a closed loop. And then the flux is defined as this, right? B dot dA. And then there are three parameters here. The magnetic field, the area, and then the angle theta between them. So we have seen that changing magnetic field very hard, and you don't have like a big, very big room, right, to change the magnetic field. The area, we just saw the motion EMF is what we discussed. Okay, you can pull a bar to the, and then by moving the bar, you can generate EMF and the current in a closed rectangle loop, but still the speed required to move that bar is ridiculous. Okay, so changing these two guys, okay, theoretically it will work. It will induce some current in a closed loop. Okay, but they're not very practical. So then that leaves us with only one option, right? Don't forget that there's another parameter here, cosine theta. Okay, so changing these two guys are hard, okay, not practical. What about changing this guy? And this is the best option, okay? So if you look at slide 13, lecture 16, okay? So it's this, what we do is this, and this is a very smart design, and this is how we generate electricity in real life, okay? So I'm not going to change this magnetic field. I'm not going to change the area of the closed loop. So I placed two big magnetic poles there to make a magnetic field, right? A north and south pole. Of course, there are two complete magnets, but we only need the north pole and south pole to generate a magnetic field in the gap, right? And then I still have this closed loop. I'm not going to change the area of the closed loop, but I can rotate the loop in this magnetic field. By rotating the magnetic, the loop in the magnetic field, right? For example, in this case, the magnetic field is from the right to the left, right? Then the angle between, so you were changing the magnet. This is the loop, right? If you look at it, so the angle between them is always changed, right? When the loop is rotating. So by changing the angle, the magnetic flux is also changing, right? And that's an easy way to change, because these two guys, they're hard to change, okay? But change the angle is very easy. You just keep rotating this loop in the magnetic field. And you don't even need a lot of space to do that, right? And then you can always get a current. But in this case, when this guy completes a one rotation, okay, the current is going to change both the direction and magnitude. So that's what we call alternating current, AC. That's why the current and voltage you get from all these wall outlets, okay, they are AC current and AC voltage. They're not going to be a constant. They're going to be a sine function, okay? So take a look at the graph on the right. So this is the current, okay, you get, that's the function of the current you get by rotating this loop in this magnetic field at a constant angular velocity. Okay, so it's going to be a sine function. Okay, so and this is how we generate electricity in real life. I do have something, a demo for that, and then you see, well, you can't see the loop. Okay, this is some magnet. Okay, bar magnet. No, U-shaped magnet. There's some loops here. So there's a crank here. If I crank it, I'm rotating the loop. So you can see the light bulb. It's going to light up. Okay. So you see, this guy is not connected to any battery. There's no battery here, right? So this electricity is going to come from the EMF induction. Okay. So hopefully you can see that. Wow, this is so hard. Wow, this is so hard. I don't know if you see the light from the. Wow. Okay. We need a new demo. But anyway, that's the idea. Okay. And I also attach a link to a YouTube video so you can watch that. It's better than this. Okay. And we are going to study AC in detail later. Okay. But this is how we, as I said, generate electricity in real life. We use a EMF induction. We use this theory, okay? But the best option is to change the angle by rotating a loop in a magnetic field instead of changing these two guys. We have seen that changing these two guys are not very practical in real life. And then the current you get from a battery, right? If you connect a resistor to a battery, that's called DC, right? Direct current, because the current always flows in one direction and then doesn't even change the magnitude. But the current you get from this is always going to be AC. Okay, so it's always going to be a sine function, and we're going to study this sine function later in detail. All right, so then in real life, well, we're not going to have like people rotating this loop, right? That's going to be stupid. Okay, so what we do is that we use some. Usually in a power station, we use a very big steam turbine. Take a look at the slide 14, okay? It's gonna extract the thermal energy from the steam, okay, and use that to do mechanical work on a rotating shaft. And then in that case, we are converting thermal energy to electrical energy, still conservation, right? And fossil fuels is the primary energy source in the world. So we use we will first convert the chemical energy to thermal energy of the gas, right? And then convert the thermal energy to electric energy, okay? And then there are also wind power, right? Because we're always trying to find the renewable and sustainable energy, and wind power is a better option because, first of all, it's almost free, right, in nature, okay? And secondly, it's clean, right? It doesn't produce any pollution, right? So in this case, we make use of the kinetic energy of the wind. We convert the kinetic energy of the wind to the electric energy, okay? And another power source is the hydropower, right? So, and this is very obvious. In this case, you use the falling water, because the falling water, when the water is falling from a very high location, then it has potential energy. Potential energy is going to convert to kinetic energy first, and this kinetic energy, fast-running water has a lot of kinetic energy. Then we can use that to convert it to rotate, okay, the loops in a magnetic field to convert that kinetic energy to electric energy. Okay, so that's another way. So as I said, this is actually a very rich topic, finding sustainable, renewable energy source. Okay. All right, so now I'm gonna tell you some application of EMF. Again, some applications of EMF induction. So first of all, I want you to introduce this concept called eddy currents. Okay, what are eddy currents? Because what we have seen that if you have a single loop, right? If you have a single loop, you place a single loop in a magnetic field, and then you change the magnetic flux through this loop some way, right? There are different ways to do that, right? You can change the magnetic field, you can change the area, you can also change the angle by rotating the loop, right? So you will always create an induced current in this closed loop. But if you don't just use a single loop, okay, you use a very big piece of metal conductor, okay, like this in slide 17. I'm not going to rotate or move a single loop in the magnetic field. I use a very big piece of conductor, okay. Either you move the magnet or you move the conductor. So as long as there's some relative movement, there will be induced currents on this conductor, right? And you don't just get one closed loop, right? You can actually have a lot of closed loops on this very big piece of conductor. Then you will have actually a lot of induced currents flowing on this conductor, okay? And they resemble, you can take a look at the image on slide 17. They resemble the eddies in a river, so we call them a new name, we call them eddy currents. It's still induced currents, right? Just a new name we use for these currents induced in a big piece of conductor instead of like a single closed loop, okay? And then what's the use of this eddy current? What's the application of this eddy currents, okay? Because eddy current, if something, as I said, in order to induce current in this conductor, there must be some relative motion, right? Either the magnetic field is moving or the conductor is moving, right? So there will be some relative motion between them. And then the eddy current, the induced current on this big piece of conductor is always going to slow down the motion, slow down the relative motion, which can be used as a brake, okay? Which can be used as a brake, okay? So I'm going to first show you a few demos so you understand why the eddy currents are always going to slow down the motion, okay? And then I can tell you some of the applications of this eddy current. So for example, here you can see that I do have a pendulum, so you can take a look at the slide 18. These are the two classical demos for eddy current. I have a pendulum, okay, this is copper, okay, this is not iron, so this guy doesn't respond to magnets, right? See that these two guys, they are magnets, okay, they are actually solenoids. You see that they are solenoids, a lot of loops, okay, so they are electromagnets, okay. So once I turn, and this is connected to well, do I miss? Okay, I'm going to plug this in. This is connected to a voltage source, okay? And then by connecting this guy to a voltage source, we can have some current in these two solenoids. They will become magnets, right? Once they become magnets, you see, then you will have a piece of copper moving in a magnetic field. So there will be some eddy currents here, induced current. Again, eddy current, just another name for this induced current on a big piece of conductor. And there will be some eddy currents here. And then the eddy currents, the induced currents, they always want to fight the change, right? What is the cause of the change? The cause of the change is the motion, right? How do the induced current fight the change? Well, you can do the 4 steps we did, right? But I don't need to do the detail. Think about it, right? The cause of the change is the motion. So instead of a slow down, instead of the fight the change, this current, this metal piece just want to slow down the relative motion, right? So this induced currents, they're going to have their own B induced. Remember these 4 steps, right? There's a change. B external, phi changes, okay? And then you need to figure out the B induced created by these induced currents, and then use right-hand rule to figure out the the direction of the induced currents. I don't need to do that. I don't need the detail because I know that at the end, this B induced is going to fight the change. How does it fight the change? Well, it's just going to slow down the motion. If the motion slows down, the changes get slower. So it's fighting the change, right? So that's why you can always see that once there's an eddy current, once there's an induced currents caused by the relative movement between this conductor and the magnetic field, the induced currents are always going to slow down the motion, even though they're not in contact. They're not in contact, you see. There's a gap here, okay? So I don't know if you can see that. They're not in contact. You now see if it's going to swing very freely because I haven't turned this on. So these two guys are not magnets yet. And remember, when I turn it on, these two solenoids become magnets, but this is copper. So it's not because like they are attracting this guy, right? I can show you, this is a big magnet. This is a big magnet, and this magnet has, this is not attracted. The copper is not attracted, right? Because this is copper. And then this paper clip, they are iron, so they will be attracted to magnets, okay? So it's not because when these two guys become magnets, they're going to attract copper. They don't, right? It's because the eddy currents, the induced currents here, they always fight the change. So they always want to slow down the motion. So it's pretty much like they're like a brake, okay? So I can show you this. I'm going to let it swing freely. Once I turn it on, it's going to stop. And they're not in contact. It's not this guy's hitting these two solenoids, no. Okay? It's because now they become magnets. There's a magnetic field here, either from that direction, this, or that direction. Doesn't matter. But I know that at the end, the induced current, they're always going to slow down the motion in order to fight the change, right? So I can do it one more time. Now I'm going to turn it on. It's going to stop, right? I turn it off. It's going to swing freely, okay? So that's one demo, okay, the pendulum demo. Another demo I want to show you that. This is also an interesting one. So I'm going to come to the front. This is a copper tube, okay? This is a copper tube, okay? This is not iron. So this guy doesn't respond to magnet, right? I do have a small magnet here, but you see there's no force between them. But this is a magnet, so it's going to attract a paper clip. See if I use some paper clip, and you see. It's going to attract paper clips, but it's not going to attract the copper, okay? So what I want to do is this. What's going to happen if I drop these magnets through this copper tube? The size of this magnet is smaller than the radius of the copper, okay? So it's not going to really be slowed down by the walls, okay? So for example, to show you that, let's do this. I'm going to drop this pencil through this copper tube. Again, the size of the pencil is smaller than the radius of this guy. So it's pretty much going to be free fall, right? It's not going to really slow down by the copper tube. So I'm going to do that here. Okay, make sure you can see that. Right? Do you see that? This guy falls really fast because that's free fall, right? Okay? But now, if I use a magnet, okay, then when the magnet is falling through the tube, so that's some change in flux, right? So this is still a piece of conductor. The copper is a conductor, okay, in a magnetic field. But now the magnet is moving, so there's some change in flux through this tube, okay? There will be induced current in this tube. And then there will be some B induced. So this guy is going to have its own magnetic field, okay? This guy is going to have their own magnetic, and this own magnetic field is always going to fight the change in the flux. How does it fight the change? It's just going to slow down the motion of the magnet, okay? It's going to slow down the motion of the magnet, okay? So watch this. And it's going to be slowed down dramatically. You can definitely see the difference. So now I'm going to drop it. Right? It's still in the tube. This is not slow motion. This is not slow motion. Okay? It's because there's a lot of induced currents in this tube. So this induced current, they have their own magnetic field. B induced, right? The B induced wants to always fight the change. The change, what is the cause of change? It's because this guy is moving really fast. Okay? How do the induced current fight the change? Well, they're gonna always slow down the motion of this guy, right? But if you see that, if I drop the magnet, again, the magnet doesn't really, there's no interaction between the copper tube and the magnet, right? If I drop this guy outside the tube, it's still gonna be free fall, okay? Right? So only because when it's inside the tube, okay, and the size is very small, so it's not because it's hidden by the walls, okay, it's slowed down by the walls. No, there's no contact. It's only because the magnetic field is changing, magnetic flux is changing. There will be some induced currents. So the induced currents, they will fight the change. They will slow down the motion dramatically. This is not slow motion, okay, this is normal speed. Okay? So that's the application of these. This is the demo for eddy currents. So as I said, if there's a big piece of metal in a magnetic field and there's some relative motion, there will be induced current in this conductor, right, in the metal. And then you don't have one current going on. You have many loop currents going on, many loop currents, right? And these loop currents, they have their own magnetic field. The own magnetic field is going to interact with the external magnetic field. The result, the relative motions are always going to be slowed down. Either the metal is moving or the magnet is moving, but the relative motion is going to be slowed down. So these can be used as a brake, right? So that they are called eddy current brakes, okay? Take a look at slide 19. So these eddy current brakes, they are widely used in trains, roller coasters. Why? Because they don't require contact. They don't require contact. So it's better than using friction. Usually the brakes there, works using a friction, right? So because the eddy current brakes, they don't require contact. They don't use friction. There's a brake. It's not going to wear out very soon, right? So it's going to last longer, right? So take a look at the image on slide 19, right? So, and then you can also, it's very easy to turn it on and off, right? So there's an electromagnet, okay? But it's not in contact with this metal disc. When the metal disc is rolling, it's not in contact. So it's rolling very freely. But if you want to break it, all you need to do, just turn on the electromagnet, okay? Turn on the electromagnet, it becomes a magnet. And then the disc is rolling, so there's some relative motion between the magnet and the conductor. There will be eddy currents, induced currents, a lot of loop currents in this metal disc. And this eddy currents is just going to slow down the relative motion between them. So at the end, the metal disc is going to stop, okay? So that's a very important application of eddy current. Excuse me. Another application of eddy current, also ENM induction, is the metal detectors, okay, in the airport, okay? I'm sure that every time, right, everyone has this experience. Every time you go through a security, they will ask you to go to a very scary box, right? And then how does the box detect the metals, okay? You say you're hiding in your briefcase or you're hiding somewhere in your body, okay? Because take a look at the images on slide 20. These two walls, they have two coils, okay? So the one on the left, we call it transmitter coil. So this guy is going to be connected to some source. So it's going to be connected to an AC source. And then when it's connected, there will be some current, right? Then there will be some current in this coil, this transmitter coil. And if it has its own current, then a loop current has its own magnetic field, right? So this guy, and it's called I naught, right? So this guy is going to have its own magnetic field. We call it B naught, right? And then if the direction is as shown in the image, so it goes to the right. Now you see that there's a magnetic field from the left to the right caused by this loop current, okay? If there's metal inside the briefcase the person is carrying, then the metal feels a magnetic field, right? So there will be magnetic flux through the metal. But if the flux is not changing, then there will be nothing on this metal. So, but because the transmitter coil is connected to an AC source, that means the current in this transmitter coil is changing. So you have a loop current, but the loop current is changing. Of course, the magnetic field it creates is going to be a changing magnetic field. So the B naught is going to be changing, right? So it's going to change either in both direction magnets. The magnetic field is going to be like this, okay? This way and that way, this way and that way. So then the metal feels a changing magnetic field. So the flux through the metal inside this, the person is hiding inside the briefcase, it's feeling a changing magnetic flux. So there will be some induced current in this metal. Okay, and they're eddy currents, right? Now these eddy currents, they're going to have their own magnetic field. They're going to have their own magnetic field, B prime. We're going to call it B prime, okay? And then this B prime is going to go through the receiver coil on the right, okay? So this B prime is also changing magnetic field because everything is changing here, right? So the B prime goes through this receiver coil on the right, and then it's going to induce I prime, the loop current on the receiver coil again. Remember, the receiver coil is not connected to a source, so there's no current there. Only because the metal inside the box now has some induced currents, a lot of loop currents there. These loop currents, they have their own magnetic field B prime, and this P prime goes through the receiver coil on the right, so that they will cause a loop current, another induced current in this receiver coil. And then once the receiver coil gets current, okay, so it detects, okay, that's some signal. It has detected there's some metal in your briefcase. And it only works when there's a metal in your briefcase, right? If there's some like something else, which is not a conductor, right? Then it doesn't matter if the magnetic field created by this transmitter coil is changing or not. It's not going to cause any induced current in anything inside the briefcase. So it's not going to really cause any current in the receiver coil. So it's not going to be there's no signal, okay? Only because only if there's some metal in the briefcase, okay? So this can detect the metal without even opening the briefcase, okay? So next time you go to an airport, you go through the security, you get in the box, you can tell them, I know the physics for the metal detector, okay? Then you look smart. All right, so we have finished this lecture. Now we're going to move on to lecture 17. Okay, we're going to move on to lecture 17. Now we're going to introduce another element, another circuit element. Excuse me. Inductor and inductance. Okay, inductor and inductance, they're very similar to capacitors and capacitance, okay? So use capacitance and capacitance to help you understand inductors and inductance. What is a capacitor? Well, capacitor, we use capacitor to store electric energy and electric charge. Remember, that's what we learned earlier, right? So, and then the capacitance is a measure of the ability of the capacitor to store electric charge and electric energy. Right, so capacitor and any two conductors, you can make a capacitor using any two conductors. Just charge them with opposite charges. They are a conductor because these are the charges they're going to stay on these conductors for later use. Right, so that's why we say capacitors, they're used to store electric charge and energy. Okay, and the simplest capacitor is the parallel plate capacitor. Right, you charge each plate with opposite sign, opposite charges. They're going to stay there, right? And then we define capacitance this way, as the charge divided by the potential difference between these two plates. Right? So that's how we define capacitance. Okay. So now we're going to introduce another element, circuit element called inductors. Okay. What is an inductor? Well, inductors are some devices we use to store magnetic energy. Okay, because magnetic field also has energy. We're going to see that. Okay, and the simplest inductor, a solenoid, right? Because you can generate a magnetic field inside a solenoid. So once if there's a magnetic field inside the solenoid, so the magnetic field has energy, you can use this solenoid to store that energy. Okay, it's pretty much like you use a water bucket, okay, to store water. But magnetic field and electric field, magnetic energy, electric energy, you don't see them, so it's really hard for you to understand that. But we can still use these devices to store the energy, right? So this is the simplest inductor, right? So we also want to define something called inductance as a measure of the ability of the inductor to store magnetic field energy, right? So that's why we define, so it's very similar to the capacitance we defined before. Now we're going to define inductance. The symbol we use for inductance is L, and the inductance is defined as this. Big N, the number of turns. Usually we make a lot of turns, right, to store more energy. So that's the number of turns of the solenoid. And then phi B is the magnetic flux through each loop, right? So you can always use the definition to calculate that. Even though sometimes, in some cases, it can be complicated to calculate, but that's the definition. And then divided by the current. Because in order to create a magnetic field in a solenoid, you have to connect it to some source so that it has a current in it, right? So there will be a current. And then this guy is going to have a SI unit, Tesla times meter squared over amp. And we do have a name for it, we call it Henry. Okay, so the SI unit for inductance is the Henry. And the symbol, you see that it's pretty much we use for inductor in a circuit. It's pretty much like a solenoid, right? This is how you draw an inductor in a circuit. Okay? All right, so this is the definition, okay, of inductor and inductance. And again, remember, what did we do after this definition? Well, then we derived the special equation for parallel plate capacitor. Right, this is only for the simplest capacitor, parallel plate capacitor, right? And then we did a lot of, solved a lot of problems with the parallel plate capacitor. We're also gonna do the same thing here. We're gonna just deal with the simplest inductor, a solenoid, okay? Because we have very good equations for solenoids. Now, then we want to derive a special equation for solenoid using this general definition, okay? So that's going to be so A is still here. Then the flux, okay, take a look at the magnetic field inside the solenoid, right? So it's all very uniform, right? And it's perpendicular to each loop. So that's why the flux is going to be B times A, right? Because the magnetic field is perpendicular to the surface, it's B times A. And the B, sorry, I'm just going to use the B times A. And the magnetic field in a solenoid, we also have a very nice equation for that, right? Mu naught times big N I divided by L, right? Then you can put everything in, okay? And the B is going to be this, mu naught N divided by L times I. You put this in, you will get a very nice equation for a solenoid, which is going to be mu naught N squared A divided by L. So this equation is equivalent to this equation, right? This is the equation for parallel plate capacitor, the simplest capacitor. This special equation is for solenoid, the simplest inductor. Okay, but this is a general definition, right? And take a look at this equation, right? So it depends only on the geometry of the solenoid. So that's why it's going to be a property of the solenoid. Once you have the number of turns, the area, the length fixed, this guy is going to have a constant inductance. Okay? It's like the capacitance. Okay. Why do we want to define this L, the inductance? Because once you have this inductance, calculating the induced EMF, induced voltage in the inductor is going to be much easier. Why? Because how do I calculate induced EMF? Well, we learned the theory, right? The theory is this. You're going to do Faraday's law, right? You're going to do Faraday's law. Faraday's law is this. If you want to calculate the induced EMF, induced voltage through any loop, you're going to do changing flux divided by changing time multiplied by the number of turns, right? But the flux is very hard to calculate, right? Well, for simple cases, we know how to calculate it, right? But perpendicular, you just do B times A. But in general, phi is going to be very hard to calculate, okay? So that's a problem if I want to calculate the induced EMF. But if you define an L, okay, the inductance, you can show that if you want to calculate the induced EMF in an inductor, in a solenoid, it's very easy, okay? So you can just do this. You can derive that. We're not going to derive that. For inductor, it's just going to be this. Okay? So, and why is this easier? You see the changing current divided by changing time. Current is very easy to measure, right? So the current goes from 3 amps to 5 amps. We have very good device to measure current. We don't have device to measure magnetic flux, right? So instead of using this is a general definition. You can always use this to calculate any induced EMF, induced voltage, right? But for a solenoid, this is much easier. Right. All I need to do is just calculate this L using the parameters of this solenoid, right? And they are easy to measure, right? Number of turns, area, you just measure the radius and the length. And then you just need the changing current and changing time, and they are also easy to measure. Then changing flux is really a pain. Okay, so that's the idea. All right, so and when we use this equation, okay, of course in this class we're not going to take a derivative, we're just going to do this. Changing current divided by changing time. And then again, the negative sign means that the induced EMF, induced current is always against the change in the flux. That's why there's a negative sign. As physicists, we always want to include as much information as possible in that equation. But when I use this equation, I always do that in 2 steps, right? When I calculate the magnitude, I'm just going to get rid of the negative sign, right? Because even the changing current can be negative if the current is decreasing, right? Forget about all the negative signs. I would just use this, right, to find the induced EMF. And now, then, if you want me to find the direction of the induced voltage or current, I'm going to use Lenz's law. Right? I'm just going to do the 4 steps. Okay? So that's the reason we want to define inductance for a solenoid. So calculating the EMF, induced voltage is going to be much easier. Okay. Now let's take a look at the example on slide 3. A solenoid used in an MRI scanner, okay, has these numbers. We want to find the magnitude of the induced EMF in the solenoid during the 30 seconds it takes to ramp up the current from 0 to its operating value of 2.3 kilo amps. Okay, so now to calculate the induced EMF, right? we can just go ahead and use this equation instead of using Faraday's law, which is the fundamental law, which is always true, right? But it's very hard to use, especially if you want to calculate the change in flux, right? Okay, we're going to do this. So first of all, I'm going to calculate the L, right? The inductance, just use all the numbers. So this area, in this case, well, solenoid, the area is going to be a circle. So this is going to be pi r squared, right? And we have all these numbers, right? The length, number of turns is 1200. The length is 2.4 meters. Right, the radius, what is the radius? 47 centimeters. Right, and the mu naught is constant. Right. Okay, you put all the numbers in. Again, try that. But this is not the final answer, right? This is only the inductance. We use the inductance to calculate the voltage. Don't forget that. This number I found is 0.523 Henry. Okay, and once you find this number, the induced EMF is easy, right? Induced EMF, you just do L it's going to be L changing current divided by changing time. So make sure this is positive, right? And then changing current, well, that's just going to be from the final minus initial. It's going to be 2.3. That's a final amp minus 0. Right? That's the changing current. Now changing time. Okay, it's going to take 30 seconds. All right, and then you put numbers in. You will find this is going to be A. Okay, you see that? That's how we use this inductance, the L we define, to calculate the induced EMF in a solenoid. It's easier than using this, okay? All right? And the electrical, because the magnetic field, as I said, we use a capacitor to store electric charge and electrical energy, right? So you can, and we derive the equation for that, right? So I'm going to write it here. I'm going to erase this, okay? So that's going to be 1/2. We derived this equation, right? C delta V squared. And we also have a similar equation for magnetic field energy stored in an inductor, okay? Which is I'm gonna write it here. So that's another equation. The UL, the energy stored in the inductor, 1/2 C. No, I'm sorry, that's not the equation. L I squared. Okay, so this is the magnetic field energy stored in an inductor. Okay, they're very similar. Okay. And then the magnetic field energy stored as solenoid, we can derive a very nice equation for that, right? Because I already have the L. This is for a solenoid, right? This is the energy, a general equation. So let's do this. I'm gonna list it here. So this is the general equation UL for any solenoid. Now because the L, I already have a very nice equation for the L. And also B, right? So I can rearrange this equation for a solenoid, right? For a solenoid, I also have the equation for B, right? So the UL for a solenoid is going to be 1/2. L is going to be mu naught N squared A divided by L, right? And the I also want to write the I in terms of B, okay? By using this equation. Right, so if you want to write I in terms of B, then I is going to be B L divided by mu naught N. Now let's plug it in here. So I would get B squared, L squared, mu naught squared, N squared. Right. And then let's do some cancellations. So I will still get 1/2, right? And then mu naught cancels this mu, so I will get a mu naught at the bottom. And the N squared and N squared cancel, right? L and L, I will still have 1 power of L at the top, and A is left, and the B squared is left. Okay? So this equation is going to be for a solenoid, right? So this equation is only for a solenoid, and this equation is also for a solenoid. This is a general equation for any inductor. This is equation only for a solenoid. Okay? This is only for solenoid, and this is also for a solenoid. Okay? And then we can define something as called magnetic field density. We do have a lot of definitions, but don't be afraid of these definitions, right? We define them because they're useful. We can define magnetic field energy density, okay, like what we did with this guy, right? We did define electric field density, which is 1/2 epsilon naught E squared, I believe. And then if you define magnetic field energy density, you're just going to do this total energy divided by the volume of this magnetic field. And then for solenoid, you see that A times L is just going to be the volume, right? This is the area. This is the length. Area times length is just going to be the volume inside this solenoid, right? And most of the magnetic field is going to be inside the solenoid. So basically, you're just doing this thing divided by A times L, which is just going to cancel this A times L. So at the end, you get another very nice equation. Very similar to that equation. You see, there are a lot of connections between E and M. So that's why at the end, we can unify them in one theory. Okay? So I'm going to this is called uniform, this is called magnetic field density. This is called a magnetic field energy, okay? So don't get them mixed up. All right, I'm gonna stop here.